I'm Jafar Safarian from NTNU. I'm professor at NTNU at the Department of Material Science and Engineering. So today I shortly present about the fundamentals, things related to the HAlMan process, and my colleague also continues with what we do in the consortium and our project. About the HAlMan, the name comes from a hydrogen aluminothermic reduction and manganese, which is in the title of the project here, sustainable hydrogen and aluminothermic reduction process for manganese and its alloys and critical raw materials production. So the key element is, of course, manganese. A bit about manganese is the fifth most abundant metal in the earth crust. It's widely used in metal alloys, mostly in commercial steels and also aluminum alloys, and it has applications also in batteries and so on. Currently, its production is accompanied with significant CO2 emissions and high energy consumption. And what we do in the HAlMan, we introduce a new process that offers a cleaner conversion of manganese oxide to manganese metal and also higher value alloys. And that is done by using hydrogen, and we do recovery of energy also for the process. Next slide, please. So we have manganese ore in the nature. You see the photo on the left is from a manganese ore pile I took. And in the ore, we have different minerals. In any ore, we have different minerals of manganese, like pyrolusite, manganite, which is hydroxide, husmanite, which is another form of oxide, not like pyrolusite, different structure, different properties, and so on. You see, we have simple and complex minerals in the manganese ores. We apply pyrometallurgical processes and also hydrometallurgical processes to extract manganese. So if we use hydrometallurgical process, we produce electrolytic manganese, a process which is expensive with a huge amount of waste production. So that is the main disadvantage of producing electrolytic manganese. If we apply pyrometallurgical processes, we produce manganese ferroalloys, ferromanganese and silicomanganese. In ferromanganese, we have three commercial products nowadays: high carbon ferromanganese, medium carbon, and low carbon. And silicomanganese alloys, they have about 20% silicon, and they are in two grades of medium carbon and low carbon silicomanganese. Next slide, please. Here you see the comparison of different manganese metal products and also the crude steel production in the world. We are close to the production of 2 billion tons of crude steel, and as you see, manganese ferroalloys currently are about 20 million tons. So they are in quantity much lower than steel production, but they are important and for this industry, for steel industry. So we should produce them in a more sustainable approach. And if we compare to the CO2 emissions in the production of manganese ferroalloys, we have more CO2 emissions in their production compared to the crude steel. So the contribution is in CO2 generation is significant. Next slide, please. Here you see the state-of-the-art technology that we have nowadays around the world in different countries for the production of manganese ferroalloys. We have submerged art or SAF technology. In this technology, we use electricity, and we charge manganese ore with carbon in the form of mostly metallurgical coal, and we use fluxes, and we do a smelting carbothermic reduction of the ore, and we produce manganese ferroalloy. It's like byproduct that usually contains some manganese, which is lost, of course, and we have some gas emissions, CO and CO2 emissions. So CO is later converted to CO2. If you click Here on the right, you see the case for ferromanganese production. High carbon ferromanganese is produced in submerged arc furnace. And on the right, you see there are several reactions where we get manganese oxides reduced and we get to MnO4. In parallel, we have a not wanted or unwanted reaction, which is the boudoir reactions, and some carbon in the process is lost to CO gas. Down in the furnace, we have a further reduction of MnO by solid carbon and manganese metal is produced. The ferro manganese that we get is saturated of carbon, and later in the dominant process, which is MOR process, we burn this carbon and we produce low carbon ferromanganese or medium carbon ferromanganese. So in this step also we have a CO2 emission. Next slide, please. Here you see the thermodynamics behind the process. If we, I don't go to the details, but in short, I mentioned that it is not possible to reduce manganese oxides to metallic manganese by using hydrogen and CO gases. So we have a limitation regarding the say, materials and the thermodynamics. But it's possible to reduce manganese oxide down to MnO by CO and H2 gases. If you click, yes, in SAF technology, what we do is actually conversion of manganese oxide to MnO by CO gas in the furnace in SAF. And then down in the furnace, we continue with reduction using carbon and we produce manganese. You click yes. But in HAlMan process, what we do is first conversion of manganese oxide to MnO by using hydrogen, and then thermodynamics says that it is possible to reduce this MnO further to manganese metal. So instead of carbon, we use aluminium. This aluminium is not expensive since we target to use aluminium scrap and aluminium containing waste like aluminium dross. So if we look at this, we don't have a direct CO2 emission from the process, from the HAlMan process. Next slide, please. Here you see a schematic of the process. What we do is that in the process we use hydrogen. It's preheated. We get hot hydrogen and it's used in a reactor to produce manganese ore. And when we do pre-reduction, we get an intermediate product where we have metallic iron and manganese is in the form of MnO. Then this manganese is smelted with using lime and at the same time aluminium for aluminothermic reduction, and we produce metal and slag products. So if we look at this compared to, yes, next slide please. Yeah, compared to SAF technology, you see on the left in SAF technology we have CO2 emission, but for the HAlMan technology on the right you see we use hydrogen, we use aluminium, and you see the gaseous product is mostly water vapor, so it's a clean process. And if you look at the reaction on the down on the right, you see we have aluminium oxide form. It's not gas, it's liquid in a slag, and then we can extract this alumina again from the slag. Next slide, please. Here you see typical sample that has been reduced by hydrogen, one manganese ore. The image on the left showed the ore in calcine form. It's antimony manganese ore, a commercial ore. And when it's reduced, you see the metal that we produce is bright particle. It's metallic iron, and the matrix is a lot of grains of oxide MnO, and there is also some impurities in the ore. So the reduced material looks like this in microscope. On the right, you see two XRD spectra. The top one shows the ore before reduction, the raw ore. It has manganese in the form of pixbite, Mn2O3, some calcite, CaCO3, and the iron is in the form of hematite. When we do the pre-reduction, we see the product is showing that the all metal in the or iron is reduced to metallic iron, and manganese oxide to MnO, and we have some oxides left in the material, which are more amorphous or in minor quantity. Currently, a PhD is doing research at NTNU in this area, the pre-reduction of manganese ores, and we do research on production of main ores that we have in different countries, in particular South Africa, and also one master students graduated in this area. Next slide, please. Here you see some typical products. On the table, you see that we can produce manganese with high purity, over 98% purity, and also we can produce manganese aluminum alloy, which is quite new. We call it in the project aluminum manganese. So aluminum of the manganese is the dominant or second minor component, but we can play with the quantity of aluminum in the metal. And also we can produce products like the ferromanganese, low carbon ferromanganese, or ultra low carbon ferromanganese. And in parallel, we can produce slags and slags with the low manganese oxide concentrations. At the moment, there is a PhD working on the aluminothermic reduction of reduced manganese ores at NTNU. Next slide, please. The byproduct of the HAlMan process, the main byproduct is calcium aluminate slag, and you see here typical XRD of calcium aluminate slag, and we have several calcium aluminate species in the slag. This slag can be processed hydrometallurgically, and we extract alumina for aluminum industry or smelter grade alumina. Currently, a postdoc is doing research in this area as well at NTNU. Next slide, please. Yes, here is a photo from the HAlMan team when we visited South Africa. From here, my colleague Maria presents the rest of the presentation.
So this is an EU-funded project, as Jafar introduced, and we have a wide partnership. So you can see it's a globe, and we have most partners from Europe, Scandinavia and Central Europe. But also we have 3 partners in South Africa. So we have Mintec, a research organization, and we have 2 manganese producers, HAlMan and Transalloy. So we're very pleased to have them on board because they sit on a lot of important manganese ores, as we will hear later on today. And then also we have a pilot partner in Australia, colleagues. So you can see here that we have a consortium which is divided into material sourcing, we have research organizations, manufacturers, we have both the aluminium industry, we have the iron industry or the foundry from the iron industry on board of Levny, and also the manganese industry then. And we also do machine learning here, so we try to make a smart process and communication dissemination. You already met Linda here today, so she is our communication dissemination manager in the project. And then we have the operators where we do the ferromanganese operators and also the ones doing pilots. And this is a 4-year project. We are halfway through now, or in the end of this year, 8 million euros in total. And you can see here what we are doing in simplified version. So we in big words, we're trying we are demonstrating a new way of producing a ferromanganese and other products, as you can see here on the list to the right, in a greener or more sustainable way by using different type of or other types of raw materials, as Professor Jafar introduced. So using hydrogen and aluminium instead of carbon. So that means that we will not have any direct CO2 emissions from this process. So if you go to the next slide. And here you can see more general simplified also graph. So what we're doing, we first pre-reduce the ore in hydrogen with 3 different technologies are evaluated, which I will present later on. Then we're taking this pre-reduced ore and we put it in a furnace where we do the aluminium reduction, the smelting. And this is done at Mintec in South Africa. Here we put in the aluminium dross and scrap as reductant. So here the material coming in is then MnO. And so it's already pre-reduced down to MNO. And from this process, we get out the products, which are two products. We have the metal or the alloy and the slag. And both are seen as valuable products in this project. So from the alloy coming out, we have demonstrated it with the steel foundry to make low carbon ferromanganese steels. This we can do because we don't put in any carbon in the process, which means that we have less carbon in the product, which is a high value product for the steel industry. And we also evaluate the use of this ferromanganese or the manganese aluminum alloys in the aluminum industry and see if they can use this product as well in their alloys or in their products. The slag, as Professor Jafar mentioned, is then this calcium alumina rich slag. We extract alumina and evaluate if we can take it back as a raw material into the aluminum process. And what we also do, the gray mud is evaluated in the cement industry, but also we extract critical raw materials from this gray mud. So we really try to extract all valuable elements from the input materials. And the aim is to have a near to zero waste process. So we utilize all streams and then also a CO2-free process. Next. And here you can just see what that, as I also mentioned, that we do machine learning to make it smart so that we can reduce the amount of experiments and then save time and money. So here you can see what we're doing then. 3 different type of reactors are evaluated for the hydrogen reduction part. So here at SINTEF in Norway, we have a rotary furnace, a plasma rotary furnace, where we use lumpy ore and reduce it down to MNO. At Calix, we have very fine ore. It's a drop tube reactor, so it's micrometer size, and it's falling through this reactor, and hydrogen gas is going upwards, and it takes roughly 2 minutes, and then it's reduced down to MNO. And then at Mintec, we are using a Jafar, or better called retort furnace. And here we also use hydrogen, of course, as a reducing agent. And here we also use lumpy material. So two types of lumpy materials are used, and then a fine material. So we have 3 different ways of pre-reducing the manganese, and we evaluate which technology is better. And then we do the smelting on all these 3 types of pre-reduced ores, and then produce the products or evaluate. Next, please. And in the project here, you can see live pictures of these reactors. So we have actually already done at SINTEF, the plasma rotary furnace, this campaign with the manganese ore there is finished. At Mintec, they're working on it now with their shaft. They already done their first campaign there. And at Calix, we will soon in January do that campaign. So we are quite well on time in the project. Next slide. And here's ton scale we're talking. And then the smelting. We have 3 different scenarios that we will demonstrate. The 2 first scenarios has already been done. So here what we have done is that we took ferromanganese slag that's discarded today and put it in as a raw material then, and then we just reduced it further with aluminium, and that was the first campaign. The second campaign was that we used pre-reduced ore and reduced it down to aluminium. And then if you click one more, but we will do a third campaign now when we're going to use pre-reduced ore again. And here you can see the process flow sheet. So the discarded slag that we use as a raw material in there after the aluminium reduction, this slag contains quite a lot of silica. So it's not so good for hydrometallurgical reduction or hydrometallurgical treatment. So we test it directly into cement if it can be used there. And this alloy is then tested by the aluminum industry. And for the pre-reduced ores, there we produce an alloy for the steel industry, and the slag is leached and alumina is extracted, taken back to the aluminum industry, and we are extracting critical raw materials from this gray mud.